Okay, this lecture will be on the QFT energy eigenstates. Finally, this lecture is actually pretty exciting. It's really the culmination of a lot of the hard work we've been putting into, and we're going to see how all that hard work and theorizing we're doing correlates very nicely with experiment and how it gives us a very deep and new, insightful picture of reality. If you've never seen before, I think you'll be very excited. This is one of the we're still dealing with a free scalar field, so we're not getting into full-fledged reality, but this gives you a strong indication of how the universe, according to physicists and quantum field theorists, is probably actually constructed. Recall, after a large number of lectures and a lot of tedious math, that this was the final formula we came up with for the Hamiltonian of QFT. We have a QFT Hilbert space, and the Hamiltonian for that, which is a very important part of any quantum mechanical system, after a lot of work, we concluded was this. It's the sum over P of omega P, A dagger P, a non-dagger P. A couple of things just to show before we get a little bit further on this lecture. The first is look at the commutator of the Hamiltonian with A dagger P. I'm just going to come up with a simple formula for that. So here's the first line of it here. Here I just expanded out the Hamiltonian. From basic laws of commutators, if I have a sum, I can pull that sum outside of the actual commutator. And then also if I have a constant multiplied by a set of operators, I can also pull the constant out, which is what I did here. Then I just have this sum over omega p and then this commutator. But this commutator with these three operators follows a very basic law, which you probably remember from quantum mechanics. You can think about it in probably about a minute, knowing the definition of the commutator. Prove this to yourself, but this is the formula. And if I apply this formula to this right over here, I get this, where I pull this A dagger out over here and leave the rest, these two, as a commutator of each other, plus I pull this operator out to the right, and I leave the commutator of this and this, which is this term over here. Now I remember my commutation relations that we derived from the previous lectures, that the commutator of AP with A dagger of P is this. This was a very important relationship that we realized was a consequence of the quantum field theory equivalent of commutator of X and P equals I from quantum mechanics that yielded this relationship for commutators between A and A daggers. So this is a delta P prime P, and the commutator of any operator, and also with those relationships was this, that A dagger of any P with A dagger of any other P, including whether P is equal to P prime, is always equal to 0. So that term cancels. So this is what I'm left with here. If I apply this delta function through this P prime sum, everything that's P prime becomes P. So that's this over here, and then everything that's P prime becomes P. So this delta function will become 1 only when P prime equals P. All the other terms will cancel, and so when I apply this sum, I just get omega of P, A dagger of P. So this relationship is important, that the commutator of H with A dagger P gives me this. That's the final result of this little slide. I can show exactly the same thing of the commutator of H with a non-daggered P, and you can just go through this argument, but it's almost identical to the other one, except there's a minus sign here. And the final result of the commutator of H with a P, get minus omega P, a P back. That's an important relationship we'll use in a little bit. Now we're finally getting to the question that we've been asking for the last few lectures. What are the eigenstates and eigenvalues of H such that, what are the eigenvalues and eigenvectors of H? In other words, we want to find those vectors E sub n such that H operator applied to E sub n gives me E sub n multiplied by some constant called its eigenvalue. Let 0, like this thing over here, this is what we actually call the vacuum or the ground state, be the eigenstate of 8 with the lowest eigenvalue, and that's called the ground state. This is how we symbolize it, very important. We have a ket symbol and then 0. I'm assuming that there is a lowest eigenvalue state. I'll show at the end, for those interested, in a very brief appendix at the end of this lecture, roughly why that's true, that we can actually prove that there has to be a lowest eigenvalue to the Hamiltonian, and that we call the ground state. It doesn't just keep dropping down to infinitely negative values. And also it can be shown that it's unique. I won't show that now. I might show that in some later course when we apply more advanced ideas of special relativity. But basically just know that this thing can be shown to exist and be unique. So 0 is considered the lowest eigenvalue, the lowest eigenstate of H that has the lowest eigenvalue. And that lowest eigenvalue we call E sub 0. So this is the formula expressing that H applied to this gives me back the same thing multiplied by E sub 0, and E sub 0 is the lowest possible state satisfying this condition, eigenvalue, eigenvector condition. Now, let's just consider, if we take that state, the ground state, which we again symbolize as 0, and we hit it with a dagger sub p. And remember, this could be any p that are the allowed p's that we've talked about in previous lectures. But let's just say we pick a particular p, and then we a dagger that with that p, this ground state. We will now show that this state, this is just a new state. Remember, this is an operator acting on a ket, so that's going to give me some new ket in our QFT Hilbert space. We're dealing with now all QFT Hilbert space. We're going to show that this thing over here is also an eigenstate of H. So this was an eigenstate of H with the lowest possible eigenvalue. And we're going to show that this thing here, this whole combination, is also an eigenstate of H. So that's the fastest way of showing that is this. Let's just hit this new state with the operator H. Well, this by definition is HA dagger sub P. I can just do this. I can change these parentheses around. And remember, from what we just showed, 2 earlier slides, I think, that there's a relationship from the commutator of H comma A dagger, and the commutator of that is this, and that's equal to omega P A dagger P. So in other words, whenever I see this thing, H A dagger P, I can just move this minus to the other side and rewrite the new expression for H A dagger, which is this over here, just coming straight from this commutator relationship that we proved. So instead of writing HA dagger, this is what this is equivalent to. I'm just distributing out this and this over the plus sign. That's what I get here. But now look at this second term. Here I have H of 0, and by definition, this 0 or this ground state is an eigenstate of this that follows this equation right over here. This part follows this part right over here. So based on this above, so I can rewrite that as the following. This stays the same, A dagger sub P, E sub 0, 0. That's just the definition of this ground state 0. And then this is just a constant, so this constant can be pulled out over here. This commutes a constant or a number, not an operator. It commutes with any kind of operator, so this E0 can be pulled out this way. And then I'll just have an A dagger sub P 0 over here, and an A dagger sub P 0 over here, and I can factor that out of both of these terms and just collect the numerical numbers, the numerical values in front of it. So omega P plus epsilon 0, this, just factor that out. And now look at what we have. Basically, if I start with A dagger sub P and 0, this whole thing, think of it as just one ket, and I hit it with the operator H, I get back the same thing again. A dagger sub P acting on the ground state 0, multiplied by some sort of number in front of it. So this, by definition, means that this whole thing is an eigenstate of H with eigenvalue omega P plus E0. So what does that mean? Well, I started with E sub 0. That's the eigenvalue of this eigenstate 0. And if I hit it with A dagger sub P of 0, I get another eigenstate, which is different than the first one. And this new eigenstate has an eigenvalue that's not E0, but it's increased by omega sub P, E0 plus omega sub P. Thus, A dagger sub P acting on the ground state is also an eigenstate of H with eigenvalue omega P more than E0. As mentioned before, since all experiments measure energy differences rather than absolute energies, we can stipulate that we measure all energies with respect to the ground state 0 energy E0, i.e. we can set E sub 0 equal to 0. So I'm not an experimental physicist. I'm not even a physicist. But just roughly speaking, if you do measurements in the lab, you can't really say this is the absolute energy in general when you do most quantum field theory experiments. You can just say energy differences. Just roughly speaking, we can look at what photons are absorbed by a given quantum mechanical system. And if a certain photon's absorbed, we say that there was that photon perfectly matched the energy difference between two energy eigenstates. You might remember that from quantum mechanics. We don't know what the absolute number of the value of the energy states were, but we say that there's some difference between those energy states that satisfied the energy of that photon. So that's a good example of why when we are in the lab, we really measure energy differences rather than absolute energies. So what we can do is just take the lowest possible eigenvalue, the lowest possible energy state of our QFT system, which we called E0, and just set that equal to 0. And then all other energies will be measured with respect to that. So that's justification for doing that. I'm not going to get into it, but there's obviously some questions there about vacuum energy and things like that, but we will not get to that level. So if I do set E0 equal to 0, then I can just state, my ground state has an energy of 0, but a dagger sub p hitting that has an energy omega p bigger than that. And omega p from the previous slide, that's what we proved. But remember, omega p by definition is the square root of p squared plus m squared. So the energy of this state is going to be the square root of p squared plus m squared, this p plus the m squared that was coming originally, if you remember this term m squared. I haven't yet proven anything or shown anything about it being mass, but that's the term that actually came originally from the Lagrangian. Similarly, if we do this twice, a dagger sub p acting on the ground state, you can spend a few minutes on yourself, and it's probably worth doing that. You can readily show that to be an eigenstate of h with 2 times this number, 2 times the square root of p squared plus m squared. And then if you do the same thing n number of times, you can show that the whole thing is an eigenstate of h also, with the energy of that eigenstate equal to n. Total number of times you hit it with this raising operator, or we'll call that a creation operator for reasons to be seen very shortly, n times the square root of p squared plus m squared. What if you do not just p, but one mode q and another mode p? Let's say, remember, we're allowed different possible momentums. So this is one possible p, this is another possible p here, just called it q. And let's say apply that to the ground state 0. Well, same argument. I won't get into, you can take a moment, pause the video and look at this, and it's probably worth just playing around with this on your own. But by exactly the same type of argument, using these commutative relationships, if I hit this state 0 with a dagger p and a dagger q, where these p and q are not necessarily the same, I also get an eigenstate of h. This whole thing is reproduced, but with an eigenvalue omega p plus omega q. And again, if I set E0 equal to 0, that is the final energy, omega p plus omega q. So it's very interesting. These a daggers, which were just kind of introduced as like a Fourier transform type thing of the phi operator and the pi operator, end up becoming significant. They're not Hermitian, so they don't correspond to any observable. But if I take a dagger sub p and I hit it with the ground state of the Hamiltonian, I can keep getting new energy states, energy eigenstates. The a dagger sub p's are called raising or creation operators, since they raise an energy eigenstate of HQFT by omega p. And the creation part might be, the word creation will be a little bit clearer in a moment here. What if I take not the a dagger sub p, but the a sub p? Well, remember this one, I'm going to apply this commutation relationship, which we showed on the earlier slide, that h, the commutator of h with a sub p is equal to minus omega p a sub p. And that will, of course, result in this relationship over here. And I'll show the same thing here. Suppose we have some eigenstate E. Let's say it's not the ground state 0 with energy E of the Hamiltonian H. So H sub E is equal to E again multiplied by this energy eigenstate E. Now let's act on this state E, which is an energy eigenstate of the Hamiltonian with not a dagger sub P, but a sub P acting on this eigenstate E. Let's see what happens when I hit the Hamiltonian on this new ket. I'm just going to follow through the argument. This thing here can be re-expressed using the commutator law like that. And just keep expanding things out. I distribute this out throughout. remember, this is one where I use where H applied to E. By definition, since E is an eigenstate of H, I just get E back multiplied by its energy value, which is E, and then I can commute these two numbers with respect to each other, because I can commute these two things with respect to each other because one is a number, the other is an operator, and I can just factor that out. And here I just result in the same thing again. I started with H hitting this entire ket A sub PE, and I get A sub PE back, but with a different eigenvalue than what I started with. And this new eigenvalue is omega p less than E. So omega p A sub p acting on an eigenstate E is also an eigenstate of H, but with the energy lowered by omega p. So this A dagger sub p raises, if you take an eigenstate, it raises it to another eigenstate with an energy greater by omega p, and A sub p lowers it by energy omega sub p. So I could do different combination of these things. I can just start with the ground state 0, then I raise it by A dagger P sub 0. I get a new eigenstate. Then by the argument that I just showed, that if I have any eigenstate of the Hamiltonian, and then I hit it with A sub P on this thing, I should drop the whole thing back to another eigenstate lowered by omega sub P. So that should give me really nothing but the ground state back. I haven't talked about any kind of potential numerical constant here, but I'm not going to get into that for now. That's the rough idea behind this. This kind of pretty idea where you start with the ground state, you can raise it or create a new state of higher energy by omega p, and then you can lower it by A sub p. You can do very similar things with different combinations of these things. For example, here I have the ground state 0. I act on it with a creation operator Q. I get a new state, and I hit it again with creation operator P. I'm going to get a totally new state, one with energy omega p plus omega q, but then I go ahead and knock that out with A sub p. So that's going to knock out this one, and I'll get something like A dagger sub q acting on 0. Again, I'm not taking note of any kind of potential numerical constants that happen here, but that's okay for what we're doing right now, etc. And you can pick any different combination. So kind of a neat little mathematical thing that happens with these A's and A daggers. And again, they all start from one eigenstate and put you in another eigenstate of H, of course. Now, recall that we defined 0 as the eigenstate of H with the lowest possible energy E sub 0. This is usually called the lowest eigenstate. And we mentioned that at the end of this lecture in a quick appendix, I will prove that there has to be a lowest. Such eigenstate doesn't go on infinitely, and we won't show, but it's also unique. We know that A sub p, so the question is, if let's say you start with 0 and you hit that with A sub p acting on 0, so what happens to that? Well, we know that A sub p takes any eigenstate of H and lowers its eigenvalue by omega sub p, but then what about if you're already in the lowest possible eigenstate 0 and you hit it with A sub p? Well, we must have to be consistent. A sub p acting on this just gives you the number 0, not the state 0. So this in basic quantum mechanics, undergrads often get confused with this versus this. This is the vacuum state, and this is just the number 0. So we must have this because we can't go any lower than this. And for the whole thing to be mathematically consistent, A sub p acting on this must give you just the number 0. And we say that if this is considered the vacuum, again, these terms will be a little bit more clear shortly here, but this ground state we sometimes call the vacuum. You'll hear the phrase A sub p, quote unquote, kills the vacuum, meaning it just makes it nothing. Nothing is even less than, quote unquote, the state of the vacuum. It's the mathematical number 0. Now, what about the momentum operator P? Well, I didn't want to put all of it in one big mathematical lecture. Last time we did a lot of math, but remember, we had some very nice arguments going back to the classical field theory lecture and using Noether's theorem, and we came up with the formula for the classical total momentum of a field as this. Recall from our lecture on Noether's theorem that due to the space translation symmetry of our Lagrangian, L is equal to the integral of Lagrangian density over all of space, where this was the Lagrangian density we came up with. There exist 3 conserved quantities when you use this Lagrangian or Lagrangian density. There was actually 4 conserved quantities. One resulted in the Hamiltonian, which was because of the time translation symmetry. And the other three conserved quantities are the x, y, and z momentum, which I just symbolize as this one vector p with an arrow over it that symbolizes x, y, and z, or 1, 2, and 3. And then based on our arguments, if you look back there, our classical field theory says that there's a conserved quantity which we call the momentum, the total momentum of the field, because it's related to space translation symmetry. And this was the formula we had. Well, just like we did with the Hamiltonian, we recognize all these symbols, phi, the gradient of phi, which we can define, and pi, and we can immediately quantize those using exactly our expressions, or exactly our definitions for phi and pi. So that's how we quantize this formula over here. We did that for the Hamiltonian. So we postulate that the total momentum of our entire field, our full QFT system, is given by this. But now with these quantities, pi, phi, del phi, etc., and p being operators acting on Ketzner QFT Hilbert space rather than numbers, like this is derived from classical field theory. Very simple natural extension, not hard to quantize this at all, and all this stuff makes sense. So we now remember that we found our problem a lot easier instead of dealing with phi and pi, which are very intuitive and physical and very important ideas, but hard to deal with sometimes mathematically when we're solving eigenvalue, eigenvector problems. We expanded phi and pi. We assumed they could be expanded or Fourier transformed, but they could be expanded in terms of APs and A daggers, and we have the explicit formula for that. So let's just do that and try to re-express this formula for the total momentum of our entire field. Let's re-express that using APs and A dagger P's. So here are just some relevant formulas written on the top. This is the formula for P. I just told you this is the expansion that we're using in the discrete expansion, kind of related to Klauber's book. And this is the expansion that we're using for pi, also kind of roughly in the form of Klauber's book in the discrete form. I'm just going to plug stuff in. You guys can pause and take a good look at this, but these are very similar mathematical arguments to what we used in the last lecture when we did it for the Hamiltonian. I'll try to go a little bit quick so it doesn't get too bogged down. You can take a moment and look at all this. So here's my expression for pi. I just took that, I threw that over here. Then I take the gradient of phi, and remember we've talked about that before, that just is really the equivalent of taking the derivative of this with appropriate vector notation maintained. So this IP comes down in front. I just changed this to P prime so we can keep track of the two different summations. This is a P summation, P prime summation. That IP just gets pulled down here. This minus IP gets pulled down here. That's a minus P prime, and then the rest stays the same. And then I can just keep cranking stuff out over here. I can pull out these 1 over omega v's, get this. The minus I gets pulled in the front. 1 over square root of 2. 1 over square root of 2 is 1/2. This omega sub p square root is here. This omega sub p prime square root is over here. And then I just do FOIL, first, outer, inner, last, kind of these regular binomial type stuff. I'm going to take this, and I get this term. Then I do the first and the last, and I get this term. This and this, I get this term. And then this, and I get that term. And then this is just like when we did with the Hamiltonian. It's tedious, but not hard. For those of you who just have some basic understanding of quantum mechanics and the type of math that goes into that, this shouldn't be that hard. It's just tedious. This part's, now I have it in this form, and I can see that there's an integral over d third x. So everything that has nothing to do with x, I can pull out of that integral and keep swinging this integral forward. And these parts, which have the only parts that do with x in each of these 4 terms, I can swing that integral right next to them and pull out everything else in the front. And I get this integral over here, this integral over here, this one over here, and this one over here. And now this is an important part from the mathematical interlude lecture. I think 6I is what it was. We showed that this integral over here very clearly was equal to this expression here, that the integral of d third x of e to the I p plus p prime x gives me v times the delta function of p with negative p prime, etc. And there's similar relationships with minus p and p minus p prime, things like that. So that allows me to simplify these terms. If you haven't followed and you're a little out of order in the lectures, please look at the mathematical interlude. We pretty clearly explain why this somewhat complicated looking formula is actually very clearly true. So I can basically take this entire term, just make it its now simple delta function. And I showed that here with each of these four terms, and they're kind of color coded. So here's what I get here. Now I have the sum over p and sum over p prime with a bunch of delta functions. I could take this sum over p prime with each of these individually. Before I do that, all these v's will cancel out, and then I can mess around with these i's. So I have an I in front of every one of these terms. That all factors out. I times I is -1. That will get rid of this I here and just make it a negative. So that's how I simplify that. And this is what I have here. And now I can finally do what I mentioned before, the sum over the p primes, using these delta functions, which force p prime to equal -p. And if that happens, these two terms will cancel. Sometimes I'll have square root of omega p over the square root of omega p, which cancels, or the square root of omega p over the square root of omega -p, but omega -p, for reasons we mentioned in the previous lecture, is actually equal to omega p. Just look at the definition of it. It's the quantity here squared plus m squared. A negative number squared is just positive, so that's why this relationship is true. So that this simplifies down to this over here. This is the formula for p so far that we have. I'm running out of room, so I just put this back up over here on this new slide. And now, kind of interesting here, you take a moment and think about this, but it's a very simple but neat argument. Look at the term sum over p of p, a negative p, this term over here. These minus will cancel, so I just got rid of the minus. Just look at this term here, sum over p of p, a sub p, a negative p. Remember always in our things, as we've talked about in the previous lectures, we only have a certain allowable values of p. They have to allow the function e to the ipx to complete an integral number of cycles throughout our experimental box. So these are discretized. And we also put a lower and an upper limit on p. And you also, if you look at those arguments, everything is negative. The amount of negative p's and positive p's are exactly equal. And for every p, you have an actual negative p in our allowable values. So because we are summing over all allowable p's with a symmetric amount of positive and negative p's, we can substitute p for negative p and just still do the same thing, the same sum, without changing the value of the sum. Take a moment and think about that. It's kind of a slick little argument. It works really well. It's pretty powerful. It comes up in different contexts in quantum field theory and math. The sum over p of this whole term then must be equal to the same sum over p, but if we take every time we see p, we change it to negative p. So here's a p, we change it to negative p. Here's a p, we change it to negative p. Here's a p, we change that to negative p. Negative of negative p is just p. So these two things have to be equal for the reasons that we just mentioned. But also remember that we can use our commutator law, which basically says that if we have a p and a q, the commutator to that is always equal to 0, and it doesn't matter whether p or these two terms are exactly the same, and whether one's or the negative of the other. So what it basically means, if the commutator of any two operators is 0, just write it out. We can just swap the two without thinking about it. We treat it almost like a real number. So we can swap a p and a negative p on this side. And if we get that, we are going, and if we take this negative, on the left side, I still have this term over here. And on this side, if we take this negative, swing it out front, and just swap these two because of what I just said, the commutator relationship, we get this, p, a sub p, a negative p. And if we just put parentheses to kind of allow us to see what things clearly, this whole thing here is the same as this whole thing here. So we basically have a situation where something is equal to negative of that something. And the only way that you have a number equal to its negative is 0. There's no other number in the world that the number is equal to its negative other than 0. So this whole thing has to equal 0. So you can take a moment and look at that, kind of a simple but somewhat slick mathematical argument. So that's what we've concluded here, that this whole term over here, which is this one right over here, remember the minuses will cancel, is equal to 0. So this whole thing is 0, which means we can cross out that. And exactly the same argument you can use for the same situation with the a daggers. If you want to reproduce that on your own, maybe pause the video and do that just so you can understand this derivation. Sometimes it's fun to do that and allow you to think clearly and feel the satisfaction of proving something kind of interesting and important. So this whole thing here cancels. This whole thing's canceled. So remember, we're trying to figure out our whole original expression for P in terms of A and A daggers. Okay, so just going to the new slide. This is the formula that we got from previously, right up here. Now, to kind of simplify this, we just do the following. So remember, again, the commutation relations. AP, A dagger P, the commutator of those two is equal to 1. Remember, this is a delta function, but if P equals P prime, and these two are the same P's, then you just get 1. If they're not equal, it's equal to 0. And of course, that means this. That's what this relationship means. So it means every time in this expression we see AP, A dagger P, we can replace that by its equivalent 1 plus A dagger P AP, which is this over here, which is what I've done here. And then if I just kind of expand things out, basically this is what I get. This part here is the interesting part. So remember when we did the Hamiltonian, we had something over here that we had to kind of wash away, either with normal ordering or as I mentioned, that it was a finite but large value if you have restrictions on P. And then you can wash away that energy, large but value for the energy when we did this by just assuming that we only measure energy differences between states. Here, we're not going to assume anything like that, but actually what ends up happening, if you look at this sum of P over P, as we've mentioned just in this argument, the P's themselves are symmetric. There's negative and positive P's, and for every positive P, there's an exactly negative P. So if you do the sum over all of P, this has to equal 0 if we stick by those allowed values of P that we've been doing in our formulation of QFT. So this thing will actually drop out without having a normal order. Some treatments, like David Tong's treatment, still talks about normal ordering. I don't think he gives the proof of this, but I think he mentions it in his argument, if I remember correctly. But for the way we presented things, we don't have to normal order. This thing will actually just drop out. And we get this final, very simple expression because these 1/2 will cancel out for P. Very intuitive and not that dissimilar to what the Hamiltonian expression was. So P is equal to the sum over P of P, A dagger P, A lowercase p. I'll sometimes forget to put the vector arrows on this. I apologize for that, but assume that they're there for now whenever you don't see them. So this is the expression that we get. Technically, is an expression for pi for p1, p2, and p3. Sometimes we just write pi. Or if you look at this as a vector, this is really a vector, and these are vectors. So this is the final expression for P. Now, let's go back. We did that little hiatus here. So let's go back and consider again this same state that we looked at for the Hamiltonian, but let's look at it now, the effect on P. So if we have the ground state 0, the ground state of the Hamiltonian, we hit it with A dagger of P, just like we did before. Let's see what happens if we hit this now, not with H, but with P. So we hit this state, and then in our QFT Hilbert space with P, the operator P, and that operator P, as we just finished proving, can be expressed in our AP operator formulation as the following. This sum over here, I put a P prime just to keep track of which P's we're talking about. This is A dagger P, and this is P prime. It's a dummy variable for the sum. I can kind of reorganize things over here and write that like as follows. Now, remember, this part over here can be re-expressed using our commutator law up over here. So that's all I did. I took this part over here and I re-expressed it like that and kept everything else the same. And now, if you remember, we argued that anytime if I expand this out, I'm going to have this acting on this, ignoring the first term for a second. And at the end of this whole string of things, I'm going to, no matter what, have AP, non-daggered, acting on the ground state. And we argue that that always has to equal 0. So this term will end up canceling out because you have an AP right next to the ground state, so that equals 0. And then this whole thing simplifies now to this. If I just apply the delta function, which is forcing within this sum P to equal P prime. Every time I see a P prime, it's going to equal P by this delta function. And I'm going to get this final formula over here, P, A dagger P. Now this is the original P that we started with, ground state 0. And this part over here is the same as this part over here. So this proves that this A dagger P acting on the ground state 0 is an eigenstate of the operator P, exactly as it was an eigenstate for the Hamiltonian operator H. So A dagger P on the ground state is a momentum eigenstate of P with eigenvalue P. What does all this mean? Well, it's starting to mean something very deep, very beautiful, and very important. We now have created and shown a pretty amazing thing. A dagger P acting on the ground state is an eigenstate of both the Hamiltonian for the QFT and the total momentum operator for QFT, with an eigenvalue, which we call E, that will be the energy of this thing, and an eigenvalue of the total momentum, P, called P, such that, now this is the relationship that we know, that E is equal to P squared plus M squared, that the total energy of our system, I apologize, this needs to have a squared, but the total energy of our system, E squared is equal to P squared plus M squared. This is Einstein's E equals M squared, E equals MC squared relationship, but now for a moving particle. This is one of the most important famous formulas in all of physics, kind of not expressed as E equals MC squared, but just over here. So we know that all real things that move in the universe, according to all of our experiments, and Albert Einstein follows this beautiful formula that it's momentum squared plus its other, but plus some number squared called a mass squared is equal to E squared. So this corresponds perfectly to an experiment where a particle of mass m is injected into our experimental box. I'll have a lot more to say in a little bit, but just very interesting to know that in QFT, out of all these balls moving on 1D tracks and naturally pushing that idea, we get to some situation where we think we've created an eigenstate of the Hamiltonian that looks like a particle in our universe. And I'll get a little bit more into what's happening here. But before we do, one more little addendum that's relatively simple, and then I'm going to get more into like what I just talked about. We should define something called the number operator, which in the context of what we've seen is not very complicated. So remember, we've realized that the Hamiltonian can be expressed with our A daggers and APs like this. Our total momentum operator can be expressed in the same way. We have this combination of A dagger P, AP in both situations. And here you multiply it by omega P, and here you multiply it by just P. And omega P ended up being the energy that we're increasing our states by. So let's just call this part over here the number operator. And we'll tell you right now that this also is Hermitian. If you take the, you could just literally take the dagger of this whole expression. And then remember, when you do the dagger of a dagger gives the original thing. And you have to flip the order whenever you do the Hermitian conjugate of things, and you'll realize that this is also Hermitian. So this was Hermitian. It has to be. It corresponds to real observable. This is Hermitian. And this new operator N, which is just built out of these parts, is also Hermitian. So this will actually correspond to a physical observable, which we'll say is the quote-unquote total number of particles in the system. Particles has a very interesting definition. We'll get to a little more of this in the end, but notice that this is Hermitian. And then let's kind of state probably the obvious, but I just want to show it to you again. Let's just say we have a state, which again is created like in this same manner where we take the ground state, in this case, hit it with, for example, A dagger P3, which we picked the one particular momentum from our allowable momentums, and then hit it with an A dagger P3 again. So we'll get some state here, A dagger P3, A dagger P3. If we just follow through the math and hit this whole state with this operator, which we now define as the number of particles operator, or the number operator, let's hit it with that. So that's what we get here. This is the other name for M. This is our initial state over here. And now we can just play around with these expressions, bring the sum out, put a parentheses around these two terms is what we get. We use our commutation relations again for this, which we've explained a few times now. So we can just re-express that like this with this delta function and these two things reversed. Then we just expand this whole thing out. The first term over here is going to be here, A dagger, A dagger, A dagger, A dagger, AP, AP, and then this original A dagger P3 0. So that's where this guy comes from. Here, we just expand the whole thing out with the delta function. Keep moving forward. The delta function forces, when we do this sum, forces P prime to be equal to P3, And so we can get rid of the sum and just rewrite this like this: a dagger p3, a dagger p3. And then now this term over here, if you look at these two, can also be re-expressed using the same commutation relations. So here's this a dagger, here's this a dagger. These two terms over here, I re-express using the commutation relations as this plus the delta. So I reverse the order of these two and added the delta function to make up for that. Still 0, and here's just the original expression here. Keep moving forward, just running out of space, so I just rewrote what we had previously up here. Now moving down to this part of the calculation. Well, now we have this part over here. If we expand this part will still stay as this part, and now we're looking at this part. This part of it over here will have an AP without dagger right next to 0. When we expand this out, it'll be right next to the ground state. But remember, we said that whenever you have an a lowering operator next to the ground state, that just equals 0. So this whole term will cancel. That gets killed. And all we have is this guy over here plus this original term. So that's what we get over here. Now we just distribute out this delta, which when we do the sum over p prime is going to force p prime to equal p3. And then that's what we get over here, plus this original term over here. So now we see this thing plus exactly the same thing equals 2 of this thing, which is over here. So what we've just kind of explicitly shown, which with a lot of lines, but nothing too complicated inherently, is that this state over here is an eigenstate of the number operator with an eigenvalue 2. So this type of state, a dagger p3, a dagger p3 acting on the ground state, is an eigenstate of n, the number operator with an eigenvalue n equals 2. And you can apply the same argument if you want to just play around with the math, which is good practice. You can create other states like a dagger p3 with a little bit of a different state, a dagger p4, a dagger p4, and you'll get terms like 3 for that. You'll find that this whole thing is an eigenstate of m, and with the number eigenvalue equal to 3 in this case. So this thing is considered to count the total number of, quote, particles in the system, and we'll talk about what that means in a second. So a couple more things, and we're going to get to kind of the big conclusion here. Just some nomenclature. Anytime we have a ground state and we hit it with things like this a dagger, another a dagger, and any combination of that, so here we're hitting with a dagger of minus p2. If you look at the allowable p states, this is kind of a negative momentum. You also have p2, and here we hit it 3 times, and here we hit it, once with the p5 operator, creation operator. Here we hit it 3 times with the p1 operator. Anything like this with any combination of this are called Fock states. I'm not a physicist, and I pretty much learned things on my own by reading, so I'm probably going to mispronounce half these names. I just call it a Fock state. I think it's pronounced a little differently, but that's just me and my English interpretation. So any of these states are called Fock states that are created in this type of fashion. We can also obviously define little sub-operators. Remember, we define the number operator as a sum over p of everything a dagger p, ap. But for each particular p, we can just say this is the number operator for this particular p. I just specifically make one p. The sum of all these will give you the full number operator. And the same type of thing for the Hamiltonian, and the same thing for the momentum. These are like little sub-operators, which are also Hermitian themselves. And these will represent the number of particles, for example, with momentum pi. So this will represent, this is another Hermitian thing that represent the number of particles. And again, I get to what we mean by particles with momentum pi. This will represent the energy of particles with momentum pi in our system. This will represent the momentum of all the particles with just pi in our system. So you can have these sub-operators also on our quantum field theory that are Hermitian and defined as this. Now, the real big part, which is somewhat obvious, but just real worth saying, a Fock state, like something created like this, basically is a simultaneous eigenstate of everything that we've talked about so far, of the Hamiltonian, the momentum, the total momentum operator, the total number of particles operators, and the sub-operators, HPI, PPI, and NPI. So it's a simultaneous eigenstate of all of these things. And then with this particular relationship, that the energy, let's say you can break it up into subparticles, you'll always find this, that the energy of that particular subparticle population, if you just look at the energy of things of particles that have momentum pi, you will get this formula, square root of pi squared plus m squared, and however many times you have the number operator npi. So if you just follow the math, this is what you'll get for these sub operators, this basic relationship. Now here we get to the interesting part. We just created this big theoretical structure, which seems to be like an obvious, not obvious, but a very natural way of how nature should be created. If you just exploited this idea of a scalar field that has to be quantized and obey certain principles. And then we came up with this big theory with a bunch of Hermitian operators. Now, the idea is we do experiments in the real world, and we have to see how our mathematical structure correlates to what's going on in the real world. And we have to know that no matter what, we're assuming this entire course that the world obeys the laws of quantum mechanics, one of the best tested theories in the history of science, if not the best tested. So I'm not an artist and I'm not a physicist. I'm certainly not an experimental physicist, but just kind of simplifying what I think the schema should be here. We have something like our experimental box, which we're just making as a huge cube that has a bunch of tiny cubes called voxels in it, but the whole thing is a huge cube, but somewhat of finite dimensions in our formulation. Then we have something where we can kind of inject something into this thing, which we call particles of various momentums and different states. We can mess around, we get multiple injectors, put multiple things in there. We can change the angle of this. We can change what quote unquote how fast things are that we're throwing into this box, but this is ultimately our box. In quantum mechanics, you do a bunch of stuff on your lab, and then you say you have a system, which is this thing over here, that's in a certain quantum state. We think everything in the universe is described like that. Even though it doesn't seem like that in our macroscopic world, we still assume that if we do some sort of measurement at a given time in this system, the whole thing is represented by some sort of quantum state. And it has all the principles we talked about in our first lecture. Then we have something called a detector, which can basically look at this box at that particular time and do a bunch of measurements of different things, depending on how experimental physicists create stuff around it. We use common sense and other principles, but I'm not going to get into the measurement issues in quantum mechanics. But the idea is we have a state, and we have detectors that can tell exactly at a particular time, measure different things about our state. In this classic kind of particle physics thing where we inject quote unquote particles into this area, various particles, various angles, and then just have a pick point in time and then look at our detectors. The classic detectors that we have in such a setup like this that you might see in a particle collider can detect a few things. One is that you may have something shooting out going in this direction, and then a click will happen on some sort of counter, and you might have one click, you might have 3 clicks, maybe in different spots, you might have 3 clicks in the same spot, and then you say that that's detecting the quote number of particles. This might be some sort of a bubble chamber where you see a track and you see a discrete track and you say that was 1 click. You see a different discrete track here and this one here, and that says 2 clicks, maybe 2 discrete tracks in just about the same area, and you say the number of clicks was 2. So this detector can detect in our quantum system the number of quote particles. This is the system, and then you have something here that's kind of like pushing a button and saying what's the value of this quantum system, and this is the number of particles. The same detector, when we set things up with particle physicists, can also detect for a given particle where it sees a track. It can also measure the energy of that same exact quote unquote particle. And particle we just say is a click on this particular device, whether it's a bubble chamber or some other way of detecting something. That's our particle. And then the energy of that can also be detected exactly at that time. And then also our detectors, this is what we have. I'm not a physicist, so I can't explain how they make this. But also these detectors can also detect the momentum of that particle, that particular particle. When you see that click, you can see with respect to that click, what is the energy of that thing that's clicking and what is the momentum of that thing that's clicking. So that's what our detector can do. It might, for example, only do 1 at a time or do all 3 at a time. That sort of doesn't matter. But the idea is it can figure out all 3 of these things. Now, this is an experimental fact, kind of stating the obvious, but it's not so obvious if you think about the principles of quantum mechanics. The idea behind everything we do in the lab is we kind of control this part, this injector stuff. Let's say we have a bunch of injectors. We just showed one here and a bunch of conditions that make things come out of like something else that we think is a particle falling into this box. We get to control this outer stuff. And let's say we're such good experimentalists that we can make the conditions perfect, that we have everything set up and then we do our injectors and we put stuff in here, and then we detect things. If we are able to fix the external conditions so that everything is identically the same, then the quantum state that we create in here is identical each time. So we do something, we detect the quantum, there's a quantum state, and then we measure it. We do exactly the same thing, we create exactly the same quantum state, and we measure it again. Remember, according to quantum physics, if we're measuring things like anything that we're measuring, theoretically, you can get different measurements. The most shocking fact of quantum mechanics is if you do everything exactly the same in your experiment, sometimes you'll get different results. And that's amazing, but that's what it is even if we do everything exactly the same, sometimes you'll get different results. That was Einstein's big objection to quantum mechanics. However, there are certain situations where you do everything the same and you experiment and you keep getting exactly the same answer over and over and over and over again. And what that doesn't mean that the quantum mechanics is wrong. It means that you actually prepared the state, the experimental state, however you did it with the injectors, you prepared it in such a fashion that it's an eigenstate of certain operators. Operators represent measurements. So there's a way you can fix things in the lab so that you put something in here, for example, and then every single time you measure the system, you only get, let's just say, one click on this detector over here. And then you do exactly the same situation again, you get one click, and you do it a billion times, and each time you just get one click. You do the experiment again, one click. Do the experiment again, you get one click. So that means that not that quantum mechanics is wrong, it means that you've actually prepared the system in an eigenstate, which means an eigenstate of that particular operator. Then you will always get the same answer. That's the one time in quantum mechanics where you don't get a superposition. You get exactly one answer over and over again. So you can do that in the lab, where you find that there's always, for example, one click, then the same exact preparation, one click, so you know you've prepared it in an eigenstate of the number of particles. Same thing in the lab. Turns out when you keep all the settings the same, and now you start measuring not the number of clicks, which was just one in this case, but let's say the energy of that particular click, and you have a way to measure the energy of that. And there's different ways in physics, which you can read about on other YouTube channels or other books. Then you also can measure the energy. And when you have exactly that same setup, you can do it in such a way that the energy is exactly the same every single time. So that for that exact same setup, you can also conclude that you've prepared things in such a way that it's an eigenstate of number of particles operator and an eigenstate of an energy operator. Then the same thing, you can also measure the momentum of exactly the same thing. You don't change the state, and you find that you always get this momentum P. So there are ways to do this in the lab that every single time you find that have exactly the same number of particles, exactly the same momentum, exactly the same E. And what this all means is that you can do things in a lab where you can create an eigenstate that's simultaneous eigenstate of number of particles, energy E, and momentum P. When you do that, you assume that you have created this thing that we've now called a particle, which we're kind of going backwards in our history of science, but we basically, knowing quantum mechanics, saying that we've created this thing. Whenever we have a state like that, we say we've created a particle, quote, of energy E and momentum P. And now if you do the same thing, you can do exactly the same thing and just change one thing on this injector to kind of ramp up something so that you still have the exact situation where you always get an eigenstate repeating over and over again. You get the same number of one particle, one energy, and one momentum. But now let's say you increase the adjusting so that the momentum is changing, and then you measure the new energy. You'll still get one particle, but a new momentum and a new energy. And when you do that experimentally, you will find exactly this relationship, that if you adjust it, you will get E squared equals P squared plus some constant number M squared. This is the relationship you'll get, that number one, if you just keep doing the experiment, one particular set of values thousands of times, it'll never change the numbers. You get one particle, one energy, and one momentum. But then if you adjust this one thing, then redo that experiment thousands of times, you'll still just get one particular momentum, one particular energy, and one particular number of particles over and over again. But now it's a different part of this curve. And the relationship you'll get experimentally is E squared equals P squared plus, off shifted from the axis by this amount, your M squared. And this constant positive number, M squared, that you observe is called the mass of the particle. The whole setup here, when you do this, is called a particle. We assume that there's something that we're injecting here, which we call a particle. We obviously have some intuition as to what that means, but from an experimental standpoint, we're just going by clicks and things like that in a quantum system. We call that setup a particle. And we always find experimentally this amazing relationship that Albert Einstein predicted before even starting quantum mechanics, that E squared is equal to P squared plus M squared. Amazing statement, but that's what we find. So that's what we define as a particle, and this is the relationship we find in the lab. But now let's just think of, we can do other scenarios as well where we have adjust the whole thing, and now all of a sudden we have multiple clicks. We might have 5 clicks here, and then 1 click here, 3 clicks over there, and then we find the same thing, that we're in an eigenstate if we keep repeating exactly that same scenario over and over again. What we'll always find is that we are allowed in our experiments, we have ways to figure out for this click what was the energy of that click, what was the momentum of that click, and how many clicks were there in this region. And you'll always find experimentally the same relationship, that the energy is equal to the square root of P squared plus M squared multiplied by the number of clicks in that direction. This is just experimental facts that we know that sound obvious but are important to understand in the standpoint of quantum mechanics. What we say in the lingo is that we have a situation now where we have multiple particles in multiple particles whenever we have this situation, and that each particle has momentum pi with this kind of relationship. So what does all of this mean? Just going to backtrack for a second. Now, just remember the biggest thing is that I'm kind of stating the obvious, but it's important, that we started with the quantum field theory. And if you look at the previous results of our quantum field theory, whenever we created this thing called a Fock state, we have reproduced this situation exactly. We have a theory which explains what the quantum mechanical system is inside this box, but we have a theory that we can create a state, which we called mathematically a Fock state, and that state is an eigenstate simultaneously of energy, momentum, and number of particles, as well as subparticles, the substates that we talked about as well. And the relationship that we found in that situation is that E squared equals P squared plus M squared. So our theory fully reproduces what we find in the lab here. And what this means is a pretty dramatic thing. It means that, and we'll get to a little bit more of this at the very end, but what it basically means is that we have created a situation where what physicists in the lab are calling a particle, we have created something much deeper that shows us the same results as a particle. If you take this further, what it really says is the thing that the Greeks always asking you, what can you break things up to, and they call them atoms, and we realize you might be able to break it up further into electrons and photons and other things. But what we actually realize is things like fundamental particles. We haven't quite gotten to electrons, but we'll do that. But just for the big principle is still the same. Fundamental particles are actually nothing but quantum fields and superpositions of quantum fields. They're nothing but balls moving on 1D tracks in this case, and some sort of superposition of that. So when a experimental physicist thinks they have one particle of a certain momentum and energy in the box, for example, what they really did by messing around with things is in some magical way took every voxel in space that this thing is made out of and gave a little bit of a stretch to the ball on the 1D track. The ball on the 1D track may be a little bit up here, down here, up there, 0 over here, down over there. And that whole constellation of things represents one particle. It's technically a superposition of those different configurations of states, that's the nature of quantum mechanics. But basically what we've now said is that more fundamental than the idea of a particle is the idea of a voxel that has a ball on a 1D track. That's really what makes up particles, which eventually makes up the universe. Pretty dramatic, and we've kind of shown that in the most interesting way, that we just started from very interesting ideas of quantizing a scalar field, balls on 1D tracks, what's the most natural Lagrangian that'll form, and then we've kind of started reproducing what we mean by a particle. One of the most amazing things in quantum field theory. The Fock states, just to play around with this because this is kind of fun and also important. So the Fock states, let's just say, remember I talked about we only allow certain momentums. This is our assumption so far in this course, and we will go back and forth sometimes between discrete and continuous versions, but for now I'm just going to show you the discrete version. So let's just say these are all the possible allowed momentums. This is momentum 0, this is momentum p1. For every p1 you have to have a negative p1. Technically there should be an arrow above all of these things, but this is the idea. And then this does not in general go on to infinity in our assumption. Remember, one of those mathematical interludes I talked about Similar in condensed matter physics, we assume that the total number of voxels equals the total number of allowable momentum states. That's kind of an assumption that I don't see in many QFT books, but I'm just assuming that here. But let's just say this is our line over here, and now we're trying to understand these Fock states. This here, one could think of as the ground state, called zero, like this, the ground state, the energy eigenstate of lowest Hamiltonian. A dagger P1 basically means that in this area, we just added one little hash mark. And of course, if you look at experimental physicists here, if this was our actual quantum state that we created mathematically and they measured that, they would find that there's quote unquote one particle of momentum P1 right over here and appropriate energy. And so all three of the clicks, the number of particles would be one, and it would be an eigenstate, meaning if they repeated it over and over again, they get the same number. The energy of this, the momentum of this would be P1, and the energy would be equal to P1 squared plus m squared, which is the quote unquote mass of this particular particle. The m squared is different potentially for different types of particles, but it's some number that's started from our Lagrangian. A dagger P3 would just be over here on this area over here. You can just visualize it as one quote unquote particle at P3. A dagger of negative P4 would just be another particle created over here. These are just good ways to visualize this. You can create more than one particle in our system by adding A dagger P2, A dagger P5, like you see over here. This is A dagger P4, A dagger P4. This would be, let's say, two particles of momentum P4. If experimental physicists measured this exact state, that's what they would find. The number of clicks in the detector would be 2, and they would all appear at the area of P4 when they measured the momentum of each of those clicks, and then the total energy would be the formula that we talked about many times. The sub-energy is the total energy. This is A dagger P3. Remember, if you hit that A dagger P3, you had a situation here, and then you hit it with the destruction operator, you just get rid of that, so you're back to this ground state. This is a good way of visualizing the Fock states. Here's A dagger P4, P4, a two-particle state, we call this. Then if you hit that with AP4, you get rid of one. That's the effect of this, and you just get this over here. There's sometimes some numerical constants here, which I'm not worrying about at all right now. If you hit it again with AP4, you get right back to the ground state again. And this is our ground state again. And now what happens again if you hit this with A of 0? Well, basically think of it, if you want to continue this visualization, as this. You actually get 0, not the ground state, but literally the state of true nothing. Not, this is called the ground state or the vacuum state, and this is true nothing. There's nothing there, a mathematical nothing. So a couple things. It can be shown, remember, that the Fock states represents the complete solution to the eigenstate eigenvalue problem of HE equals EE. So thus the Fock states form a complete basis for our QFT Hilbert space. We have everything very well defined. I always get struggled with a lot of different books. I feel like they didn't show how it's a natural extension of quantum mechanics, but I spent a lot of time doing that. And we talked about this initial way we defined our total Hilbert space, or a QFT Hilbert space, or a huge Hilbert space, was the tensor product of these local Hilbert spaces. And the local Hilbert spaces were just this ball on a 1D track, and you can define the Hilbert space as the potential positions of the ball. And when you take the tensor product, the whole thing, you get a configuration, meaning that if you look at one ball on one 1D track, you have one particular configuration of every ball. That's just one basis element. Then you have a different slightly configuration. That's a different basis element. If you take all of them, that whole set is the basis that we define. That's how we define things. You might want to call that, I don't think I did before, but the quote unquote the field configuration basis. That's the mathematically well-defined way of giving a basis for our whole Hilbert space. But remember, every Hilbert space, you can use a different basis. And here we've come up with a different basis where we just use the Fock states. We showed that all of the Fock states satisfy this equation, the eigenvalue eigenstate equation. So every one of them is an eigenstate of the free Hamiltonian for a QFT scalar field theory. I didn't necessarily show that it's complete. In other words, could there be another eigenstate which I didn't show? I'm not going to do that, but it is the case that the Fock states form a complete basis, meaning that they represent the complete solution to this equation. So therefore, they have to form a complete basis, because this is an complete eigenbasis of a Hermitian operator. So let's summarize what we've done. A lot of big things here. We started by imagining that at every point in space is a point, or I call it a ball, but it's really a point on a 1D track. If you take a breath and kind of look back at everything, there's a lot of math, a lot of stuff, but inherently simple and beautiful. Starting with that picture, we quote unquote derived what the most beautiful Lagrangian or Lagrangian density should be. How? We used the most absolutely beautiful principles of physics, Einstein's theory of special relativity, the idea of locality, and the idea of just being simple. A lot of Dirac's type of, I don't call it Dirac's, the guy who invented simplicity, but he definitely hammered it home. Then, using that, we quantized our system in the standard way. We didn't create like a new type of set of laws. We still believe in the laws of the universe or quantum mechanics, and that's what we use to quantize our system. And then we also, in addition to all the standard stuff, remember this very basic law from quantum mechanics that the commutator of position and momentum operators IH, or is equal to I in units like we're assuming where H or H bar is equal to 1. Nothing crazy we did here. We started with that physical picture and then used regular quantum mechanics and everything else to come up with this, to keep moving. Then after that, we got a Lagrangian density, and then using Noether's theorem, we realized we converted L to H, and or H, the density of H, the Hamiltonian density, and then integrated that to get the full Hamiltonian. So then we got our quantum system Hamiltonian, and we use all this stuff here to get the resulting Hamiltonian for this particular quantum system, which I'm calling now the free scalar field, which is just the ball on the 1D track. We're going to get to a little bit more complicated systems later, but still same exact ideas that help describe more realistic particles that we are familiar with, like electrons. But for now, just for mathematical simplicity, we're just doing the free scalar field. This explains a lot of the big ideas about quantum field theory. The resulting Hamiltonian for this free scalar field was better solved. Instead of dealing with the way that's more clearly defined, we then realized we can quote unquote Fourier transform our initial operators, phi of x and pi of x, in terms of these things called A and A daggers. And that ultimately, through some mathematics that was somewhat tedious in the previous lectures, gave us a new form for the Hamiltonian of QFT. It's this in terms of A and A daggers, this simple formula. Then, once we have the Hamiltonian in this form, then we can solve the eigenstate eigenvalue problem for the Hamiltonian. And our solution to this much more simpler equation yielded eigenstates that are Fock states. And the Fock states, remember, are created by A and A, or A daggers acting on the vacuum state or some combination of that. Those are Fock states. These Fock states were not only eigenstates of HQFT, but simultaneous eigenstates of other things like the total momentum operator, the total number of particles operator, the sub-operators HPI, PPI, NPI. And what we realized is that if we look at that within this, the eigenvalues that happen when you look at this of these eigenstates satisfy these equations that we're very familiar with when we think of things in terms of number of particles in the lab. So what we are basically have said that if we go into the lab and then experimental physics use the terms particles, and we look at situations from an experimental standpoint, we can perfectly identify what they are identifying as a particle as our number operator for our quantum field theory system that we developed mathematically. We can define what they call the energy of the particle as our Hamiltonian of our QFT system. What they call the momentum of that particle is what we define as the momentum for our QFT system. And if you identify each of those, we say that our mathematical system that we created fully represents what they have in the lab. And what we're saying then is, again, rather profound, that we have this lab situation. But now what we're saying is what the physicists for years have been seeing as, quote unquote, what an experimental physicist has been seeing for years in the lab as an elementary, quote unquote, particle is not really the fundamental constituent of nature. Photons, electrons, again, we're going to get to a little bit of nuances to get more exact descriptions of photons and electrons, but just follow me for now. But the things that we've been taught are the fundamental constituents of nature are actually not. What really is going on in nature is every quote unquote fundamental particle is actually built up itself out of lots of little voxels. And within each voxel, there's a ball moving on a 1D track. So it's the ball moving on the 1D track and the whole constellation of them in space that looks like what we always thought was a fundamental particle. So one particular configuration is a ball on 1D track, quote unquote, might represent one particle, but that's actually not correct. We have to say a superposition of different types of those configurations represents that. But the basic idea is what is truly fundamental. If you ask the questions that the Greeks asked thousands of years ago, our answer now in 2026 is that every, quote unquote, the most fundamental thing in nature is a ball on a 1D track within a voxel. And we'll refine this idea a little bit to see things like electrons and photons and eventually everything that is then known to exist like quarks, but this is the basic idea. You can stop right there. I just have a quick little appendix, which is a part just showing one thing that we assumed, and even this has a little bit of stuff that we're not being complete, but just for those that are interested for a quick minute. Remember, I started with an assumption that there has to be a lowest energy eigenstate of H, but does there always have to be? Not really. Theoretically, you can say the energy eigenstates can go on negatively for an infinite amount. I'm just going to do this briefly. You can take a quick look at this, but it just has to do with this particular fact that, let's say we pick a particular P, we have HP is equal to A dagger P, AP, omega P. This is one particular sub value of this Hamiltonian operator. Same thing with the number operator over here, A dagger P, AP, and we have this relationship over here. Let N be an eigenstate of HP and NP of unit norm. So we're assuming that the eigenstates of HP and NP can be normalized. Have more to say about that, but the answer is yes, they can actually be normalized, even though that might not be fully obvious and probably needs to be demonstrated. I'm just going to assume that. Assuming that, then you have, if they're normalizable states, you have this N with its inner product of itself is equal to 1. If you just follow through this, you have HP of N is equal to omega P, NP, N. This is the definition. This is how you can re-express this operator using just the standard formula. And then since this is an eigenstate of that, you get N omega P N. And then now let's just say you consider, knowing this simple fact, you consider this where you take the inner product of this with its bra. So this expression over here. You do the same inner product right over here. And then you can swing out this omega P because it's a number and keep the you do this over here for this over here, and then this, you just use the same formula that you know for HP, put it right on over here. Don't look at this part yet. So HP is equal to omega P, A dagger P, AP. You can swing out the omega P out to the front, and then you get this expression over here. But look at this thing over here. This is going to be equal to this over here. So this becomes N omega P, and the N and the omega P can be swung out this way. Then you have the norm of N and N, which we are assuming is 1. So that becomes 1. So this side becomes omega P dot N. Here you still have this formula over here. These omega P's will cancel. Look at this thing over here. This is really the heart of this proof. You have the bra N, and then A dagger P, AP, and then the ket N. And what this is, if you think about it, is just the formula for this ket, APN, right over here. This is just a ket in our Hilbert space. If you take its bra, you have to just kind of invert everything, and you make this a bra, and then make this thing its dagger, so you get this part over here. So this is basically just a bra with its corresponding ket, which is what we define as the norm or the norm squared in quantum mechanics. That's what this is over here. But according to the rules of our Hilbert space, and quantum mechanics says everything is a Hilbert space, the norm of any vector, we didn't really get into this in the quantum mechanics lecture, but this is more details. But in quantum mechanics, everything is defined by the Hilbert space, and mathematicians define the Hilbert space as always having one, in addition to other conditions, that the norm of any vector, which is this definition here, has to be positive semi-definite, meaning that it's greater than or equal to 0 for any vector. And this is in particular one vector in the system. So that means that this quantity over here, which is this norm over here, has to be greater than or equal to 0, which means that N has to be greater than or equal to 0, which tells us that there has to be a lowest possible ground state, both in terms of the eigenvectors to the number operator and the Hamiltonian operator. So N has to be greater than or equal to 0. It can never be negative. It's just a simple proof. That's it. Thank you.